All right, welcome to another WebAssign discussion. In this case, we are in section 7.5, talking strategy for integration. So this section really brings together all of the integration techniques that we've seen in this course at this point. U-sub, integration by parts, trigonometric substitution, and partial fraction decomposition. And we're going to be looking at all of these techniques juxtaposed to one another, having to decide when to use what. Unlike whenever you're doing section 7.1 homework and you knew integration by parts was coming up every time, integration by parts could come up in any of these 13 exercises. So could trig sub, so could u sub. We'll just take it one bite at a time. So what about this expression here? Hey, that looks like a classic trig sub, doesn't it, right? Because when you got a square root with a degree 2 polynomial inside, that's a classic trig sub scenario. Unfortunately, u sub won't work for us here because the 1 plus x squared does not have its derivative 2x hanging out within our integrand. Right, what about this? Hey, this is another u sub scenario, right? Square root 1 minus x squared. Here, what, x equals sine theta, I believe, is our substitution, because what, 1 minus sine squared is cosine squared. Right, hey, here's a trig integral. Because the sine power is odd, right, when you have sines and cosines, if either of them are odd, you set u equal to the other one. So we would do u equals cos x here. I believe that would work out. So u equals cos x, yeah, would do the job. Yeah, this is interesting, right? Because I want the u to be my inside function x plus 5. But if I set u equal to x plus 5, okay, hey, that'll work actually, right? Because if we set u equal to x plus 5, we'll be able to write this guy as square root u, that factor of the square root x plus 5. Now, letting u be x plus 5, du is just dx, so that's simple. The dx swaps out for du. But now what about the x squared? The x squared can be found because if u is x plus 5, solve that for x. X is just u minus 5. And you can put the u minus 5 squared in front. So substitution will work really nicely here. We've got the inside function of x plus 5. If this was an x squared plus 5, we'd be using trig substitution. But since this is just x plus 5, I think substitution is the way to go. Right, 3 integrals are given that although they look similar, require different techniques. Evaluate the integrals. Okay, this first one is u sub straight away, right? Because 1 plus x squared, that works really nicely with the fact that upstairs we've got its derivative, well, 3 times its derivative upstairs, because the derivative of 1 plus x squared is 2x, 3 times 2x is 6x. Life is good there, letting u equal 1 plus x squared. In the second case, we can't use u sub, but we can use inverse trig, because factoring out the 6, we just have 1 over 1 plus x squared, and that's cookie cutter inverse trig. In the bottom case, I think we will have to use a partial fraction decomposition, because 1 minus x squared factors out to be 1 plus x, 1 minus x. This is a great exercise, by the way, because you see u sub, you see a cookie cutter inverse trig, and now you see a partial fraction decomposition. Fortunately, this shouldn't be too bad, because 1 over 1 minus x and 1 over 1, or excuse me, a over 1 minus x and b over 1 minus x shouldn't be too tricky to resolve, since we just have the a and the b, and since we just have linear factors downstairs. So nothing too sophisticated there. 3 integrals here as well. All these involve the ln function. Okay, so let's see. Because we have the x in the denominator, we can use u sub in this first case. The u equals ln x, the derivative of ln x is 1 over x, and so the 1 over x would be taken into account by our du. And so, hey, this is going to work out really nicely, because I think what dx is just going to be x du. And so the x's would cancel, and life will be good there. So u sub in the top case. In the second case, oh boy. Right. I think we're going to have to use integration by parts, because, yeah, unfortunately, unless you know the antiderivative of the ln function, which I think is like x ln x minus x, but that's not common knowledge, I don't think. You'd probably use integration by parts, and using integration by parts, we just set u equal to ln 2x. And then you could factor out the 2, and then dv is dx. The last one would be integration by parts again, because u equals ln x, logarithms are high on the priority scale as far as integration by parts goes. Letting u equal ln x, then dv in this case would like be x dx if we factor out the 2. If we don't factor out the 2, the dv would be 2x dx. Right, oh yeah, nice. This is a good array here. So some trig integrals, sine squared. Hey, the sine squared is when you only have even powers of sine and cosine, you got to pull one of those double angle formulas that you'll always be given. I think in this case, the sine squared identity is like 1/2 times 1 minus cosine 2x. That's going to be our sort of trig identity of choice. With the sine cubed, though, when you have odd powers of sine and cosine, you're going to set u equal to the other one. It seems twisted here, but you're going to let u equal cosine x. Letting u equal cosine x, you will have 2 powers of sine unaccounted for after you cancel one of the powers of sine when you compute du. But the additional 2 powers of sine will be able to be replaced with 1 minus cosine squared, which would just be 1 minus u squared. So it seems weird to let u equal cosine x in this case, but that will actually be just the ticket. This is a long assignment, by the way. I'm going to try to speed up here, but I'll go as fast as I can. The last one, that's pretty cookie cutter. I guess if you want to use u sub, you'd let u equal 2x, but we've seen an integral like this many, many times. What function has a derivative of sine 2x? That's just what, 1/2 minus 1/2 cosine 2x. So the 2 will actually intermingle with that 1/2, and I think you'll just get minus cosine 2x. Not too bad. Right, evaluating this integral, this feels like a u sub integral. Downstairs, the 6 minus sine x is your u, and then the derivative is going to take account of the cosine x upstairs, and life will be good there. I wish we could do u equals x cubed plus 3x, but we can't. We're going to have to use a partial fraction decomposition here. Factoring the denominator, the x is going to factor out, and then you get an x squared plus 3. The x squared plus 3 is an irreducible degree 2, and so you'll have a over x plus bx plus c over x squared plus 3. And we'll have to take the steps of partial fraction decomposition by writing a common denominator with our a, b, and c expression, equating numerators, and because we have the quadratic factor downstairs, we're going to have to do this sort of old school and collect degree 0 coefficients, compare them to minus 3, collect degree 1s, compare them to 2, and collect degree 2s, compare them to 0. We'll have 3 equations, 3 unknowns. Hopefully one of those equations is not too bad. Looking at this one here, my gut instinct is u sub off of the fact that we've got the 5 minus x inside our exponential function, right? And when you have a function inside another function, that tends to be u sub friendly, and in fact that will work out here, right? Because if u is 5 minus x, or 5x to the minus 1, the derivative of u is going to be essentially x to the minus 2, which will take into account this x squared that's downstairs. So u sub is going to be the way to go here with u equals 5 over x. While this happens to be a definite integral, so be it, that's fine. When we do our u sub, we can just convert our bounds from x to u, and then that'll save us having to take our antiderivative function all the way back to x. What about this one here? Powers of tangent and secant. If memory serves me right, oh, and this one's not too bad at all. When you have even powers of secant, you'll just let u equal tangent, and actually letting u equal tangent will take care of both of those powers of secant. You won't even need a trig identity here. This is just good old-fashioned u substitution. And so when you convert everything in terms of u, rather than having to go back to theta, you might as well convert your bounds in terms of u as well, and that'll save you a step. Right, evaluating this one. Oh, goodness gracious me. Oh, this is gosh, this is a trig sub, right? Because I almost want to let the 81x squared plus 1 be my u, but if we let the u be 81x squared plus 1, the derivative of that is 2x, which is not, we don't have a 2x upstairs. The x is downstairs, which is really x to the minus 1. So really the only way to go about this is to use a trig sub, and I think the trig sub we want here is x equals 1/9 tangent theta. I think 1/9 tangent theta will do it, because 1/9 tangent theta when squared will be 1/81 tangent theta. The 81s will cancel, and you'll get tan squared plus 1 inside the square root, which is good for business using the trig identity. So, yep, this is a trig sub. Right, every elementary function has an elementary derivative. Oh my goodness gracious me. I would have to really think about this one. let's see, because it is true that every elementary function has an elementary derivative, but it is not true that every elementary function has an elementary antiderivative, because 1 over x has an antiderivative of ln x. Ln x is not an elementary function, it's transcendental. I think, gosh, this is a weird question. I wish it wasn't here. I'm pretty sure the first one is true and the second one is false. I'll tell you what, let's just nail this down, because that's kind of a ridiculous question. My instinct is what I said previously. Yep, and that is right. And well, maybe my example was not even accurate, but well, there we are. So let's call that a video for a discussion of section 7.5. It was a long one, but frankly, this is excellent integration practice. Sorry for the coughing. This is excellent integration practice. Seeing all of these integration techniques juxtaposed. If you can do this exercise comfortably, you're getting yourself well prepared for the final exam. That's for